So let's think about how we can figure out the order of growth or the big O of a given algorithm. So we've learned that the big O is based on the dominant factor in the running time, but we also said we're not going to calculate running time. So how can we figure what the dominant factor of the running time is if we don't know what the running time is? Well, the answer is that we can just examine the code and look for certain constructs that affect the running time. We don't need to actually calculate the running time. The biggest culprit that drives efficiency is loops. So loops are the big things you want to think about. Now, here's some things to keep in mind when figuring out your big O. Consecutive blocks of code, so that means blocks of code that follow each other, meaning you do one whole block and when that's done, you move on to the next block. These are considered separately. So what you need to do is you need to evaluate each block on its own and then you add them all together. And then the highest order one is going to win out in terms of the big O. Okay, this essentially means that if what I'm about to say describes your algorithm, do one thing, finish up, then do something else. In these cases, you add together the running times. Okay, so if you have two loops, but they're consecutive, then you're going to figure out the efficiency of one loop, figure out the efficiency of the next loop, and whichever one is worse or higher, that's the one you'll use for the whole algorithm. Okay, so if they're separate consecutive blocks, you add them up. Now, again, loops are often the driving factor, and loops are often dependent on the size of our data set, meaning they're based on n or our array.length or our list.size or however our data set is represented. So whenever you have a loop, that's where you want to look for what's driving your order of growth. So how many times is that loop going to run relative to the size of the data? Okay. Now, nested loops will also obviously affect our big O. In order to figure out a nested loop, you have to think about how many times the inside loop runs, how many times the outside loop runs, and that means that the statements inside the nested loops will run inside times outside. So this is like a multiplication of growth. Okay, so if your algorithm is do something one full time for every single time you do something else, like in a nested loop, in this case, you multiply the runtimes together. Okay, so if you have, again, two consecutive loops, you would add their efficiencies together, highest one would win. If you have nested loops, you need to figure out the efficiency of the outer loop, the efficiency of the inner loop, and then you'll actually multiply them together, and that will be your big O. Now, one thing you have to be careful about is methods inside of loops. So our same rules apply. If you have a loop and then you have a method inside of a loop, you want to think about the efficiency of that code inside, even if it's a call to a method, and multiply it by the outside. So for example, if you have a method that is order of n and you call it inside of a loop that runs order of n times, that whole loop is going to be O of n squared. So even though the loop itself is only running n times, if every time it runs, the code inside calls a method that also runs n times, that whole algorithm is going to be n squared because you've got n for the loop, n for the method, and you multiply them together because they're nested. Okay. Now you have to really carefully consider the efficiency of methods that you didn't write. So when you're invoking methods inside of loops, you always want to be thinking about what is the efficiency of this method? Because if I'm writing a loop of order n and I'm invoking an order n method inside, then I am writing n squared code. And again, if that is code going to be used only for a small data set, that might be okay. But if you're writing code that is meant for a large data set, that is not going to be okay. All right. Now, good documentation of methods will describe the efficiency of non-constant methods. So if you take a look, for example, at the ArrayList page, it tells you which methods run in linear time and constant time, so you can always know the efficiency of the methods you're invoking. So good documentation like that that's provided in the Java Standard Library will let you know the efficiency of these non-constant methods. But it's just something you have to be really careful about because it's kind of easy to just see a loop and think, oh, yeah, it's just a loop, so it's order n, and not think about the fact that the code inside is also order n, and so the whole thing is n squared. One other thing we need to think about with big O is that we describe the worst case running time or execution time of an algorithm. So this should say can, we can evaluate the best case, the worst case, or the kind of average and expected case, and the efficiency can be different depending on the input. We usually don't care about the best case because we can't ever count on the best case happening. So we usually don't care about that. We usually care about the worst case. And that is often the same as the average or expected case. So oftentimes the worst case scenario will be the same as our average scenario. And a lot of times, if they're different, that will be specified on the API page, kind of saying, average case is this, but worst case, it could be this. But in general, we think about the worst case when we're using running time in terms of what we report about the efficiency of an algorithm. So let's actually look at some examples. So what I strongly encourage you to do is look at this code, pause the video, and before you go on, pause the video and figure out what you think big O is, and then play the video again, and I'm going to walk through it together. So take a minute, pause the video, look at this example, and try to figure out big O. Okay, so let's look at the code together. So we've got a nested loop, right? We've got a for loop here and a nested for loop here. So we know we're going to be using multiplication, right? So we're going to have to figure out how many times the outer loop runs and how many times the inner loop runs. So all of our loops here are based on the size of our array. So this outer loop is going to run n times. The inner loop is going to run n times. And now let's look at the code inside. Well, I've stated here that this is code independent of n. So that means it's code that doesn't depend on the size of n. So it might be like a print line or something else, or it might be some call to a method that runs in constant time, something that's independent of n. So what that means is that the code here is constant, right? If it doesn't depend on n, it would kind of be, order of 1. So because these statements are nested, we can now multiply. So we get n times 1, and this algorithm is n squared. So when you have a nested loop like this, where both loops depend on n, and your code inside does not depend on n, then your efficiency is going to be n squared. Let's take a look at another example. So pause it, figure out what you think big O is for this. So for this one, I again have two loops. I have a for loop here and a for loop here, but these are not nested, right? This whole entire for loop completes before we start this for loop. So we figure out the efficiencies separately. So here we look at this loop. Well, this is dependent on n, and this is code independent of n, so that's 1. So the efficiency of this whole thing is just n. And for down here, again, this loop is dependent on n. Inside, it's not, so that's just 1. So the efficiency of this whole part is n. And we said that when you have consecutive groups, you add them together, n plus n, which is 2n, but we ignore the coefficient. So this algorithm here is going to be order n. It increases linearly as our problem size increases. All right, take a look at this one. Okay, in this case, we have 3 loops, 3 nested loops, 4, 4, and 4. Let's take a look at the outermost loop. That's going to run n times. Let's take a look at the second loop. That's going to run n times. Let's take a look at the third loop. Well, that's not dependent on n. That's going to run 100 times. And then inside the loop, that's code independent of n, so that's going to be order of 1. And because these are all nested together, we're going to multiply them. So we're going to do n times 100 times 1. So that's going to be 100 n squared. But of course, again, we drop the coefficient, so the big O of this is just n squared. So you do have to be careful with loops. You can't automatically assume that 3 loops means n cubed, right? Because you have to make sure that which loops depend on n. That's what will drive it. So here's another example. Okay, so again, we have 3 nested loops. And this code is definitely missing some closing brackets there. So here, our first loop is order n. Our next loop is order n. Our third loop, again, is order 100, so that's going to be constant time. But now I've said that the code that's being invoked here is order n. So maybe this is another loop, or maybe it's a method call that's order n. It's something that's order n. So now I need to say that this part of the code is order n too. Because these are all nested together, I multiply. So I'm going to get n times 1, or you can think about it, or 100. It doesn't really matter because we know we're going to drop it, times n again, and that's going to be n cubed. So this algorithm is n cubed. Okay. Here's another one. We're using an array list in this one, so pause it and note that you might have to open up the array list API page to see what the efficiency is of that method. So figure out what you think the big O is of this algorithm. Okay, so here we've got a loop that is going to run n times, and inside we now need to know what this code is. Well, in order to know what this code is, I need to know the efficiency of the get method. So if I open up the ArrayList API page and I read this documentation at the beginning, it tells me that size is empty, get set iterator, and list iterator run in constant time. Tells me a little bit about the add, and then it tells me that all the other operations run in linear time. So the one I care about right now is get, which runs in constant time. So that means this whole algorithm is going to be n times 1, which is just order n. Now here's another one. So again, we need to look at the API page for ArrayList, and what we'll see is we want to invoke that contains method. And as I said here, these other methods run in linear time. So what that means is this outer loop is n, but the contains method is also order n. And because this is happening inside of a loop, it's nested inside, we multiply. So this whole algorithm is going to be n times n, or n squared. All right. So there's a couple examples. Hopefully you're starting to get the idea of kind of what to look for. You want to look at loops. You want to look at whether those loops are consecutive or whether they're nested. You want to pay close attention to method calls that happen inside of loops, or method calls in general. And in doing those things, that's how you can figure out the efficiency, the big O. Now, one last word. I want to make one last word about big O in the real world. So we are obviously talking about kind of theoretically figuring out the efficiency of an algorithm, and that is critically important. But there's two things to keep in mind. For small data sets, inefficient algorithms are actually okay. Okay, so if you have an inefficient algorithm, but you know your data set's always going to be small, then maybe you can use that inefficient algorithm. It might not matter. If your algorithm is n squared, n cubed, but you know you're only ever going to have a data set of size 100, then it's probably okay. You don't need to think about optimizing that and making it better. But if your problem size might grow larger, then it's not going to be okay. So keep that in mind for small data sets. The other thing to think about with a data set is that there are some data set sizes where a linear algorithm might be faster than a constant time algorithm. Like, let's say your running time of your constant time algorithm was 10,000 statements, and let's say your running time of your linear algorithm was just 2n, and let's say you have a data set of size 10. Well, if you were to actually figure out the running time, the constant algorithm is going to take 10,000 units of time. The order n, which has a running time of 2n, is going to take 20 units of time. So for some small data sets, a linear algorithm could actually be faster than a constant time algorithm. Similarly, a quadratic algorithm might be faster than a linear time algorithm. Because remember, we're not measuring how long an algorithm takes. We're measuring how the execution time grows, the rate of growth. So for some small data sets, it might be possible that algorithms of a worse efficiency are faster. But as the data set size grows and grows and grows, that's not going to be true anymore. Okay, because the constant time is never going to change, and our linear one is just going to grow and grow and grow. Okay, so keep these things in mind for small data sets. The other thing to keep in mind is that in the real world, the constants do matter. We've just been saying that we drop the constants when we're evaluating big O, and that is true. That is how we evaluate big O. But in the real world, you do need to think about that. So if you have an algorithm whose running time is 5n and another one whose running time is 100n, well, these have the same big O, right? If I ask you on a test which is more efficient, a running time of 5n or running time of 100n, you should say they're equally efficient because they're both big O of n. These are both linear algorithms. But in the real world, if you have a choice between these two algorithms, pick the 5n, right? Because in the real world, the 5n is going to finish quicker than the 100n. Okay. And again, this relates back to the idea that we're not measuring execution time, we're measuring growth. So the reason these are equally efficient is because they're going to grow at the same rate. When I double my size of n, this algorithm is going to increase at the same algorithm that this one does. So the change in execution time is going to be equal. But in terms of actually how long this thing is going to take to run, obviously 100n is going to take longer to run than 5n. So again, when you're thinking about just big O, you ignore those constants, you ignore those lower order terms. But once you are thinking about actual execution time, then you do want to try to minimize those things, right? You would want 5 loops instead of 100 loops, even though the loops are consecutive. Okay. So keep these things in mind as you're evaluating big O, but then also when you're actually writing code, you will need to think about the big O, but you also need to think about these kind of, extra sort of real world situations in trying to develop the most efficient and the quickest code that you can.